Right now, as you read these words, something is unfolding that almost no one on Earth is aware of. A machine roughly the size of a small car is traveling through a region of the universe where no human has ever looked, no probe has ever reached, and no scientific model has ever managed to accurately predict what's there. This isn't a new spacecraft. It isn't a product of modern engineering. It was built before the internet existed, before home computers existed, before most of the scientists now studying its data were even born. It operates on about 4 watts of power. For comparison, the small bulb inside your refrigerator draws more electricity than that. And this ancient, tiny, underpowered machine, one that was only ever designed to last 5 years, is currently sending us information about the universe that is shaking the foundations of modern physics. The researchers analyzing its data aren't using words like interesting or unexpected. They're using words like astonishing, baffling, and we were wrong. This is the story of Voyager 1. And here's the part the headlines aren't telling you. It isn't just what Voyager 1 discovered out there that should keep you up at night. It's what it discovered out there that directly bears on the survival of life right here on Earth. It's what's happening to it right now in 2026 that almost nobody is discussing. And it's what's going to happen in just a few months. A date already fixed on the calendar, marking a moment no human civilization has ever reached before. Stay with me, because by the end of this, you'll never look at the night sky the same way again. I'm Your Name, and this is your channel. Subscribe now if you want more stories like this, because we're just getting started. Let's rewind to the beginning. September 5th, 1977. A rocket launches from Kennedy Space Center in Florida carrying a spacecraft named Voyager 1. Its mission is simple and modest. Fly past Jupiter, fly past Saturn, capture some photographs, gather some measurements, and then drift off into space and fall silent. Its expected lifespan is 4 years, maybe 5. NASA anticipates wrapping up the mission around 1981 or 1982. It would be a successful little trip. A nice postcard from the outer solar system, and then quiet. What actually happened is one of the most remarkable things in the history of science, and most people have no idea just how remarkable it truly is. Voyager 1 did not fall silent. It passed Jupiter in March 1979 and beamed back the first close-up images of that planet's surface ever seen by human eyes. It passed Saturn in November 1980 and kept going, picking up speed along the way, using each planet's gravity like a slingshot to gain more velocity, more distance, more territory. By the end of the 1980s, Voyager 1 had already traveled farther from Earth than any object humanity had ever launched into space. And it was still transmitting, still sending its faint signal across the expanding void, still gathering data, still running on hardware that modern engineers look at with disbelief. Then, in 2012, 35 years after launch, something happened that made the whole story suddenly much larger. Voyager 1 crossed the heliopause. If you've never heard that term, it's the single most important boundary in our entire cosmic neighborhood. And crossing it is equivalent to stepping outside everything our civilization has ever called home. Here's how to picture it. The sun doesn't just give off heat and light. It continuously releases a stream of charged particles known as the solar wind. And this wind blows outward in all directions, pushing against surrounding space and forming a massive protective bubble around our whole solar system. That bubble contains every planet, every moon, every asteroid, every comet, every spacecraft we've ever launched, and every living thing that has ever existed. The outer edge of that bubble, the point where the solar wind finally loses its energy and is stopped by the pressure of interstellar space pushing back from the other side, is called the heliopause. It marks the actual physical boundary of our solar system. Everything inside it belongs to us. Everything outside it is something else entirely. In 2012, Voyager 1 crossed that boundary and emerged on the other side. It became the first object in human history to leave the solar system. Not a metaphor, not a technicality, but the first physical object our civilization has ever sent into the actual space between stars. And then it kept transmitting. Think about what that means. We currently have a live instrument sitting in interstellar space, not orbiting a planet, not drifting in the outer solar system, not lingering near the heliopause, actually inside the dark, cold, ancient space that lies between star systems, a space that no scientist, no telescope, no ground-based model has ever been able to directly observe from within. And it's sending us data about what that space is truly like. What it's telling us is not what anyone expected. Here's where the story's first twist arrives. For decades before Voyager 1 got there, scientists had built detailed mathematical models of what interstellar space should look like. Not guesses. Serious, peer-reviewed, rigorously tested models constructed by some of the sharpest physicists alive. And those models all told roughly the same story. Interstellar space, the plasma between stars, should be relatively calm and smooth. A thin, cold, sparse environment where particles drift slowly and not much happens. A kind of cosmic waiting room between star systems. Voyager 1 entered that waiting room and found it was actually a storm. Starting in 2017, the plasma wave instrument aboard Voyager 1 began picking up something nobody expected and nobody could immediately explain: a persistent narrowband emission. A kind of faint but constant hum in the fabric of interstellar plasma that, according to every model built to describe this environment, simply shouldn't exist in the way it does. Not a one-off burst, not a spike that could be brushed off as a glitch, a continuous signal year after year, spanning a distance of over 900 million miles of interstellar space. For perspective, the distance from Earth to the Sun is 93 million miles. This emission has been detected across a stretch of space 10 times longer than the distance between our planet and our star. Scientists studying the data, published in the peer-reviewed journal Nature Astronomy, were unambiguous in their conclusion. Interstellar space is not the calm, uniform void the models described. It's turbulent. It has structure at every scale, from distances measured in meters up to distances measured in millions of miles. In a physical sense, it's alive with motion and complexity that had been completely invisible to us because we'd never had a single instrument inside it before. Now pause and sit with that for a moment. Every model built to describe our universe beyond the solar system was constructed from the outside, looking in, from a planet, using telescopes, mathematics, and theory. And now, the first instrument we've ever actually placed inside interstellar space is telling us that those models were missing something fundamental, that the universe beyond our solar system is more complex, more dynamic, and more structured than we understood. But here's where this stops being abstract and starts being personal. Because those discoveries about interstellar space don't stay out there. They reach back here. The same bubble separating our solar system from this turbulent interstellar environment is the bubble protecting life on Earth. The heliopause isn't just a line on a scientific diagram. It's a shield. It deflects the most dangerous forms of cosmic radiation, the high-energy particles streaming in from distant exploded stars, keeping them from reaching the inner solar system at full strength. If that shield turns out to be significantly weaker or more unpredictable than our models suggest, the implications for biology on Earth would be enormous. And what Voyager 1 is telling us is that the interstellar environment pressing against that shield from outside is more turbulent, more variable, and more energetic than any model has accounted for. We don't yet know exactly what that means for the long-term stability of the shield itself, but the fact that we now have to ask the question at all marks a shift in how we understand our own vulnerability as a species. Now the story takes a stranger turn. Because before we get to what Voyager 1 found right at the boundary itself, we need to talk about what happened in 2023. Because in 2023, Voyager 1 nearly died. For 5 months, the spacecraft kept transmitting a signal back to Earth, but what it was sending was gibberish, corrupted code, scrambled data that the engineers at NASA's Jet Propulsion Laboratory, despite decades of experience reading everything the spacecraft had ever sent, could not decode. The instrument was still alive. The signal was still arriving. But whatever it was trying to say had become unreadable. For a team that had been successfully running this mission since 1977, this was unlike anything they'd ever faced. The cause, once they finally identified it, was both simple and devastating. A single memory chip inside the spacecraft's flight data system had physically degraded after nearly 5 decades of constant exposure to cosmic radiation. One small piece of 1970s hardware, a fraction of an inch in size, had developed a fault that was corrupting the section of software responsible for formatting and transmitting scientific data. No alarm had sounded. No warning had been issued. The chip had simply failed quietly after 46 years of non-stop operation in the harshest environment any human-made object has ever endured. In an ordinary engineering situation, you'd fix a broken component by going to it and replacing it. In this case, the component was 15 billion miles away, unreachable by any known mode of transportation, with no repair mission feasible on any relevant time frame. The only tools available were radio signals moving at light speed, and even those took 22 hours one way to reach the spacecraft. 22 hours just for a message to arrive, another 22 hours for a response to return. Every diagnostic step, every attempt to investigate the problem, every test of a possible fix required a minimum wait of 44 hours to complete a single exchange. Consider what that engineering process actually looked like from inside the control room. You examine a piece of data. You form a theory about what might be wrong. You draft a set of instructions to test that theory. You transmit them. You wait 22 hours. You receive whatever the spacecraft sends back. You analyze the response. You find something slightly different from what you expected. You form a new theory. You write new instructions. You transmit them. You wait 22 hours again. You repeat this process, step by patient step, for months. And every moment of it carries the awareness that a single wrong instruction, sent once across 15 billion miles of void, could permanently end the mission with no chance of recovery. The JPL team worked through this for months, carefully and methodically, under a kind of pressure most engineering scenarios never produce. And they succeeded. They determined that the corrupted code couldn't be repaired, but it could be relocated. The affected portion of software was broken into smaller sections and stored in different areas of the spacecraft's available memory, each section individually checked and rewritten to function correctly from its new location, then carefully reconnected to work as a whole. It was, in effect, remote brain surgery performed through a 44-hour time delay on a nearly 50-year-old machine sitting 15 billion miles away. In mid-2024, Voyager 1 came back online and resumed sending clean, readable, complete scientific data. And what it immediately went back to transmitting was more evidence of those persistent, unexplained plasma oscillations in interstellar space, more measurements of the turbulent structure the models had never predicted. The spacecraft that should have died in 1981 had come back from what could have been its final silence, and it returned with more to tell us. But none of that, not the discovery, not the near-death experience, not the recovery, prepared anyone for what Voyager 1 had actually found the moment it crossed the heliopause back in 2012. Because this is the part of the story that the scientific papers describe in language that stops sounding like physics and starts sounding like something else entirely. For decades, the models describing the heliopause, the outer edge of our solar system, predicted what crossing it should feel like to a passing instrument. The solar wind gradually thinning on the inside, the interstellar medium gradually becoming detectable on the outside. A slow, smooth transition from one environment to the other, a gentle blending at the edges, like where a river slowly meets the sea. That is not what Voyager 1 found. At the heliopause, particles weren't calmly thinning out. They were moving at speeds approaching a significant fraction of light speed. They were colliding at energies generating temperatures near 30,000 degrees Celsius. Not inside the sun, not in any star, but at the outer edge of our own solar system in what was supposed to be relatively cold, sparse transitional space. Some researchers have described this region as a wall of fire, and not as a metaphor, but as a genuine concentration of ultra-energetic charged particles forming a physical barrier at the edge of everything we call home. And then came the magnetic discovery. For decades, one of the foundational predictions about crossing the heliopause was that the magnetic field environment would shift dramatically. Inside the bubble, the sun's magnetic field. Outside the bubble, the entirely separate magnetic field of the galaxy. Two distinct environments with distinct magnetic personalities, cleanly separated at the boundary. Voyager 1 found something entirely different. The magnetic fields on both sides of the heliopause were, in ways existing theory hadn't predicted, connected. The sun's magnetic field lines, carried outward by the solar wind and compressed at the boundary, were interacting with the galactic magnetic field beyond it through a process called magnetic reconnection, where field lines from different sources rearrange themselves and release energy. The solar system and the surrounding galaxy aren't magnetically separate. They're magnetically linked. At the boundary between everything we know and everything we haven't yet explored, there's a zone where energy is being exchanged between our home and the wider cosmos, in ways no model built before Voyager 1 crossed that boundary had accounted for. This isn't a footnote. This isn't a minor correction to existing theory. If the relationship between the solar system and the interstellar environment is more dynamic, more connected, and more energetic than the models described, then our understanding of how the heliosphere shields Earth across geological timescales needs to be rebuilt from the ground up. Now let's talk about what's happening right now in 2026, because the story isn't over. In fact, it may be entering its final chapter, and the timeline is tighter than most people realize. Earlier this year, NASA made a decision nobody inside the mission wanted to make. The low-energy charged particle experiment, one of Voyager 1's scientific instruments that had been gathering data almost continuously since the spacecraft launched in 1977, was switched off. Not because it stopped working, it was still functioning fine. It was shut down because Voyager 1 is running out of power, and there was no longer enough to keep it running. Voyager 1 draws its power from three devices called radioisotope thermoelectric generators, essentially containers of plutonium-238 that generate heat as the plutonium slowly decays, heat that gets converted into electricity. At launch, these generators produced around 470 watts of power. Today, nearly 49 years later, they produce roughly 250 watts. They lose about 4 watts every year. At some point in the early 2030s, output will drop below the minimum level needed to run any remaining instrument, and Voyager 1 will go permanently silent. The team managing the spacecraft has known this was coming for years. Long ago, the scientists and engineers sat down together and worked out a careful plan for which instruments to shut off, and in what order, to squeeze as much scientific value as possible out of the dwindling power supply for as long as possible. Of the 10 scientific instrument packages Voyager 1 carried at launch, 7 have already been turned off. Decisions about what to shut down and when are among the hardest choices a scientific team ever has to make, because each lost instrument represents a set of questions that will never be answered. Because there's no way to turn an instrument back on once you've decided you switched it off too soon. But here's the twist. Almost nobody outside the JPL mission team is discussing. They haven't given up on buying more time. NASA engineers are currently working on something reportedly referred to internally as the Big Bang procedure. It's an experimental attempt to restructure how power is distributed across Voyager 1's remaining systems, aiming to extract additional electrical capacity from components currently running below their potential efficiency. The idea is technically complex and carries real risk, since even small changes to how power flows through a nearly 50-year-old spacecraft with no manual override available could produce unpredictable results. So the team is doing what careful engineers do, testing the procedure first on Voyager 2, which carries slightly more available power and sits somewhat closer to Earth, making a potential failure somewhat less catastrophic. Tests on Voyager 2 were scheduled for May and June of 2026. If those tests confirm the procedure is safe and effective, the same approach will be attempted on Voyager 1, with the earliest possible attempt scheduled for no sooner than July of this year. And here's the detail that makes that significant. If the procedure works, there's a real chance the low-energy charged particle instrument, the one just shut down, could be switched back on. The team is being cautious. They're making no promises, but they're still trying. Because with Voyager 1, assuming things are finished before they actually are has never once aged well. And now comes the moment already fixed on the calendar. The one that's already certain, the one no human civilization has ever reached before, and one that will arrive whether or not anyone is paying attention. On November 18th, 2026, at 16 minutes and 12 seconds past 2 in the morning, Pacific Standard Time, Voyager 1 will reach a distance of exactly 1 light day from Earth. That means it will be so far away that a signal moving at the speed of light, the fastest anything in the universe can travel, will take exactly 24 hours just to reach it. If you send a command to Voyager 1 on a Monday morning, you won't know if it arrived until Tuesday morning, and you won't get the spacecraft's response until Wednesday morning. 2 full days of waiting just to complete a single exchange of information. No human-made object has ever been that far from Earth, not once in the entire history of civilization. And on that date in November 2026, Voyager 1 will cross that threshold for the first time while still alive, still transmitting, still sending back data, and then it will keep going. Every hour it travels roughly another 38,000 miles deeper into interstellar space. The communication delay will keep growing, the power supply will keep shrinking, and at some point in the 2030s, the last signal will come. But even when that happens, Voyager 1 doesn't stop. There's nothing in interstellar space to stop it. No friction, no atmosphere, no gravity strong enough to meaningfully alter its course. It will simply keep moving silently in a straight line at 38,000 miles per hour into darkness, with no end on any human timescale. And bolted to its frame, attached to the body of this dying machine, is something that will outlast all of it. The Voyager Golden Record. A gold-coated copper disc carrying greetings spoken in 55 human languages, the sound of rain falling on a forest, the sound of ocean waves, the sound of human laughter. 90 minutes of music drawn from cultures across the whole span of human civilization, diagrams explaining the basic principles of our physics and mathematics, and a map built from the positions of pulsars designed to show whoever finds it exactly where in the galaxy our planet sits. Carl Sagan, who helped design the record, called it a message in a bottle cast into the cosmic ocean. And that's precisely what it is. Because whoever or whatever eventually finds it, whether that's another civilization a million years from now or some form of intelligence we can't currently imagine, the record will tell them something true, that a species existed here, that they were curious, that they reached outward, that they built a machine out of metal and electricity and mathematics and launched it beyond everything they had ever known, carrying the sound of their own laughter. The record will still be traveling when the sun becomes a red giant and swallows the orbit of the Earth. It will still be traveling long after every human city, every human archive, and every piece of stone we ever carved our names into has been erased by geology and time. It is the most permanent thing our civilization has ever created, and it's riding on a spacecraft currently running on less power than the light above your bathroom sink. Now let's return to the science, because there's one more thing Voyager 1 is doing right now that deserves to be at the center of this story. The persistent plasma emission it's been detecting since 2017 isn't just an anomaly. It's, according to the researchers analyzing it, the first continuous real-time measurement of interstellar plasma density humanity has ever obtained. Before Voyager 1 began detecting this emission, scientists could only take isolated snapshots of plasma density in interstellar space, measurements triggered by specific events, like shocks produced when massive eruptions from the sun traveled all the way out to the heliopause and sent ripples into the interstellar medium. Those measurements were valuable but scattered, like trying to understand the weather across an entire continent by checking a single thermometer once a year in one city. What the persistent emission from Voyager 1 provides instead is something closer to a continuous feed, a running portrait of interstellar plasma as the spacecraft moves through it day after day, year after year. And what that portrait shows us is that interstellar space isn't a static, uniform backdrop. It has texture, it has weather, it has structures built from charged particles and magnetic fields stretching for millions of miles, interacting with the outer boundary of our solar system in ways that Earth-based models couldn't detect or predict. The space between stars isn't empty. It's full, it's active, it has a physical character we're only now, for the first time in human history, beginning to actually read. There's a question at the heart of all this that the scientific community hasn't yet answered. The persistent emission has two possible physical explanations, and researchers working with Voyager 1 data haven't yet determined which one is correct. The first possibility is that the emission comes from thermally excited plasma oscillations, the natural vibration of plasma particles interacting with their surroundings. This would be a genuinely significant discovery, but it would fit within existing physical frameworks without requiring them to be rebuilt. The second possibility is that what Voyager 1 is detecting is something called quasi-thermal noise, a different physical mechanism that carries information about plasma density and temperature in a subtly but importantly different way, one that would require existing models of the interstellar medium to be substantially revised. Settling this question requires either additional data from Voyager 1 itself, which is producing less of it every year as more instruments go offline, or a new mission specifically designed to study interstellar space with instruments built for exactly this purpose, capable of making the measurements needed to resolve the question. No such mission currently exists. No such mission is currently funded. The next spacecraft capable of reaching interstellar space and crossing the heliopause, even if funded and built and launched today, wouldn't arrive at that boundary for at least 25 years, meaning that when Voyager 1 finally goes silent, the question it raised will remain open. The map it began drawing will stop being updated, and the only real-time window our civilization has ever opened into interstellar space will close and stay closed for decades. That silence is coming. The exact date isn't fixed yet, but the direction is. Every year the power drops. Every year more instruments go offline. Every year the team at JPL makes harder choices about what to keep running and what to let go. And sometime in the early 2030s, the last instrument will hit the minimum power threshold, and the final signal will begin its 24-hour journey home, arrive, be recorded, and there will be nothing after it. After that, Voyager 1 will simply keep moving silently at 38,000 Hawk, carrying its golden record through the darkness, passing through regions of space that human eyes won't reach for tens of thousands of years, continuing the journey that began on a morning in September 1977, when a group of engineers pointed a machine at the stars and pressed the launch button expecting it to last 5 years. Here's what I want you to take away from all this, because there's a fact buried in the middle of this story that's easy to miss when you're focused on the discoveries and the physics and the engineering. Right now, in 2026, the only live scientific instrument humanity has ever placed in interstellar space is 48 years old. It was built with technology that predates personal computers. It runs on less electricity than the bulb above your kitchen stove. And it is sending back information that is reshaping how we understand the universe and our place within it. We've built things that are far larger. We've built things that are far more powerful. We've built things that cost far more money and involve far more complex technology. And none of those things have told us what Voyager 1 is telling us right now, because none of them had the one thing Voyager 1 had, the audacity to keep going long enough to actually get there. There are questions about the universe that can only be answered from inside the universe, not from a ground-based telescope, not from a satellite in Earth orbit, not from a mission to Mars or the asteroid belt, only from a machine that crossed the heliopause and entered the space between stars. We have exactly one such machine. It's old and dying and running on 4 watts of power. And as long as it's still transmitting, we need to be listening. Because when it goes quiet, the answers to some of the most important questions we've ever asked will go quiet with it, at least for a generation. The signal is still coming, stretched across 15 billion miles, delayed by 22 hours of travel time, carrying information about a universe that is stranger, more turbulent, more connected, and more extraordinary than any model built from Earth ever correctly described. One machine, 4 watts, one chance to listen. The question is whether anyone is paying attention. If this kind of story is what you come here for, subscribe right now and turn on notifications, because we're going deeper into the edges of what science actually knows next time. Drop a comment with what surprised you most in this video, and share this with someone who needs to hear it, because this story deserves more than the silence it's getting. Thanks for watching.